Alrighty, howdy folks. Section 3.4, chain rule. Simply put, quite possibly the most important section in this entire course, Calculus 1. You must, by the time you finish Calculus 1, you must have mastered chain rule. The reason is, everywhere this will start to show up. Okay, you get into Calculus 2 or differential equations everywhere, or some of your engineering courses, you would have to take the derivatives of things where you will be applying chain rule. Okay, now without much further ado, let's get into it. First, I'll try to give you a formal definition, but if you don't understand the formal definition, don't worry too much about it. I'll give you plenty of examples. Okay, if u is a function of y, but y is a function of x, and they are both, say, differentiable functions, which ones, u and y, that is f of y and g of x, they are both differentiable functions, then you can say this: du dx is du dy times dy dx. Okay, so notice we have u as a function of y, y as a function of x, so u is indirectly a function of x. Directly, u is a function of y, but because y is a function of x, u is in fact a function of x. In fact, if you wanted to, you could say u is f of g of x. You know that composite function? So u is f of g of x. In that case, how do you find du dx? And the answer is, figure out the derivative of u with respect to y, and then multiply that by the derivative of y with respect to x. That is what chain rule is saying. Okay? I hope you got it. However, I will address it in a slightly different way. It is related to this, but I think this is much more efficient way of doing it. So we know that ddx of x square. Maybe I should point out at this time. See, this is precisely why I like this concept of ddx, because I can now, for example, show you du dy, and I say, what does that mean? That means d dy of u. You see, that makes so much more sense. d dy of u, meaning the derivative with respect to y of the quantity u. In the same way, the derivative with respect to x of x square. Oh, we all know that is 2x. Cool. Now if I ask you, hey, what is ddu of u square? Hey, come on, man. That's exactly like ddx of x square. So that's got to be 2u. Yes, you're right. Now I got an interesting question. What is ddx of u square? Right? And here the idea is ddx, we need to differentiate with respect to x, but a function of u. Well, in that case, the chain rule can be interpreted as, take the derivative of u square first with respect to u itself. Okay, but be sure to multiply by du dx, that is ddx of u. Cool. If you understand this way, I'll give you plenty of examples. Boy, you will be effortlessly doing chain rule. Okay, let me repeat that. To find the derivative with respect to x of something like a function of u, first take the derivative of that function of u with respect to u itself. Whatever it's a function of, it's a function of u. Okay, take the derivative with respect to u. But because we actually need to find the derivative with respect to x, be sure to multiply that u itself, the derivative of u itself, with respect to x. Cool. And sometimes du dx, well, this is nothing but du du is u of u square is 2u. So this is 2u du dx. I might write this as u prime sometimes. Okay, du dx is the same as u prime, meaning derivative of u with respect to x. But I prefer this 2u du dx in many situations. There are situations where I like 2u u prime, but in the chain rule part, I like the du dx part. Cool. Armed with this, I'm going to show you quite a few interesting things. Okay, what is ddx of x to the n? Oh, that's a power rule, nx to the n minus 1. You know this. Now if I say, what is ddx of u to the n? Right? Isn't that kind of like this problem? Yeah, so you take the derivative of u to the n with respect to u first. So I'm not even writing this du of u square, but I am actually doing that. So figure out the derivative of u to the n with respect to u. Oh, which is nu to the n minus 1, right? But don't stop there. The key is, do not stop there. You must multiply this by du dx. Cool? Next, we know ddx of e to the x equals e to the x. I'm writing these things because I want to relate it to something that you already know. And just make a small change to what you already know, and you got the new thing mastered. So ddx of e to the x is e to the x. So I'm going to ask you, what is ddx of e to the u? So you need to differentiate e to the u with respect to u, figure out ddu of u, e to the u, which we all know, if ddx of e to the x is e to the x, ddu of e to the u would be e to the u. So as a first step, yep, you just say e to the u. But do not forget what? To multiply that by du dx. Cool? Are you getting the hang of this? Move on to the third one. ddx of sine x equals cosine x. Based on the pattern, can you guess what I'm about to ask you? Yes, you got it, I think. I'm going to ask you, what is ddx of sine u? Cool. What is it? The answer is, first take the derivative ddu of sine u, which is cosine u, based on this result, times, do not forget, be sure to multiply by du dx. Cool, folks? Let me see. Oh, I got a few more, looks like. ddx of tangent x is secant square x. So what's the question? What is ddx of tangent u? And what is the answer? ddu of tangent u is secant square u, don't stop, times du dx. ddx of cosecant x is negative cosecant x cotangent x. ddx of what? Cosecant u is negative cosecant u cotangent u times du dx. Did all this make sense? Fine. But once we understand this concept, let's actually try to solve some problems like the ones that you have in your book. ddx of some x squared plus 2x minus 9, the quantity raised to 5. No, what? You might be wondering, how's this related to what we studied? Right? In the previous slide, we talked about these kinds of things. What does that got to do with ddx of some x squared plus 5x plus 9, the quantity raised to 5? This is what I want to say to you. When you look at this, does it look like a simple x to the 5? If it were a simple x to the 5, we know answer is 5x to the 4. The derivative of x to the 5 is 5x to the 4. The moment it is not a simple x and it is something more complicated, raised to the power of 5, just tell yourself, I'm going to treat this guy as u. Did you get it? I'm going to treat this x squared plus 2x minus 9 as u. So this to me now is looking like d dx of u to the 5. What is d dx of u to the 5? Well, what is d du of u to the 5? 5u to the 4. What is u? Oh, u is the stuff inside the parenthesis, x squared plus 2x minus 9. So 5 times x squared plus 2x minus 9, which is our u, to the 4. Right? As a first step, that's what we do. We look at this as u to the 5. Cool. The derivative of u to the 5 would be 5u to the 4. However, we need to do what? Multiply by du dx. Now, I'll be more precise about what I mean by du dx. Du dx means d dx of u. But remember, what is u? This guy, x squared plus 2x minus 9. So d dx of that x squared plus 2x minus 9. That's what you multiply by. Cool? Well, this one, just write down the first part exactly the way it is. What is the derivative of x squared plus 2x minus 9? The derivative of a sum equal to sum of the derivatives. So derivative of x squared is 2x. The derivative of plus 2x is just 2. The derivative of 9 is 0. So we have 2x plus 2. That's what I said. Done. That's it. Isn't that cool? All right. What did I do? I factored out a 2. I factored out a 2 and why is it like this? I'll fix that. I factored out a 2 to make this into x 2 times x plus 1, and 5 times 2 is 10, and so that's why you see this x plus 1 here. All right? Okay, d dx of what am I saying here? E raised to the whole thing, x squared plus sine x is in the exponent, is up on the top. Okay? Are you with me? E raised to the whole quantity is x squared plus sine x. It's not like e raised to x squared and with a plus sine x. E raised to the quantity x squared plus sine x. That makes it slightly more interesting, more challenging. Cool. How do I look at it? I look at it as I see e to the something. Is that a simple e to the x? No. Well, if that is the case, I'll call that as u and say I'm looking at e to the u. What is u? X squared plus sine x is my u. Keep that in mind. If you need to, write down on the side, hey, u equals x squared plus sine x for me right now. Okay? And so d dx of e to the u, we did that in the previous slide. First take the derivative with respect to u itself. E to the u, the derivative is e to the u. Oh, so as a first step, e to the u happens to be x squared plus sine x, e to the x squared plus sine x. What else do we need to do? Multiply by du dx or d dx of u. U happens to be this exponent. So d dx of, I didn't even bother to say like here, times, folks, d dx of u. I just went ahead and straight away did it. And I want you to get that good at chain rule. So times d dx of this guy, x squared plus sine x. Can you differentiate x squared plus sine x effortlessly? By now you should be. X squared, the derivative is 2x, plus derivative of sine x is cosine x. So end of the story is times 2x plus cosine x. Alright, I'll do plenty of examples. Alright, now we have d dx of cosine of the quantity e to the x minus tangent x. the way you should look at this is cosine of something. Okay, it's not a simple cosine of x. The moment it is not a simple cosine of just a simple x, think of it as u. So cosine of u. What is u? The stuff inside the parenthesis, e to the x minus tangent x. So the derivative of cosine of u with respect to u is, ask yourself, what is ddu of cosine u? Negative sine u, right? So we have as a first step, negative sine of e to the x minus tangent x. Cool? Then we must multiply this by du dx or ddx of u itself. U is the stuff inside the parenthesis. What's the derivative of the stuff inside the parenthesis that we need to multiply by? Oh, the derivative of e to the x is just e to the x minus the derivative of tangent x is secant square x. Ta-da! Are we done? You bet. That's it. So this is negative sine of e to the x minus tangent x, negative sine of the quantity e to the x minus tangent x, and the whole thing multiplied by e to the x minus secant square x. Cool. Next, ddx of sine square x. Now, this is a very interesting case. The reason I say that is, the moment we saw, let's go back to every one of these previous ones. Looking at this, I could tell, hey, this is like u to the 5. Here, what is this like? Oh, this is like e to the u. What is this like? Cosine of u. What is this like? Sine of u? No. Dang. What is that like? Oh, Dr. Sam, you're just making a mountain out of a molehill, man. Come on. ddx of sine square x is... give me just a second, please. Alrighty. Sorry about that. I'm back. So I was saying, so ddx of sine square x. Am I making a mountain out of a molehill here? That's simple, man. That's just cosine square x. If derivative of sine x is cosine x, derivative of sine square x must be cosine square x. Big tan not equal to cosine square x. Okay. Okay. Now, what is ddx of sine square x? Well, the way you need to look at any, please pay attention to this. If you are taking the derivative of any trig function raised to a power other than 1, okay, sine square x, sine cube x, cosine to the power of 5x, or tangent to the 5/3 x, all these things, whenever a trig function is raised to a power other than 1, you must think of it as the trig function raised to that power. That means we tend to write this as sine square x, but what we actually mean is sine of x, the quantity square. So first be sure to write it like that. Sine of x, the quantity square. All right. Any advantages of writing it like this? What I mean by that question is, notice, going back to this, we said this looks to me like ddx of u to the 5. This looks like e to the u, cosine of u. So what does this look like? This should look to you like u square. Just as the first problem, this looks like u to the 5 with u being this polynomial. Here, the u happens to be sine x. Okay, so ddx of u square. Well, then we are in business. ddx of u square. Oh, piece of cake. What's ddu of u square? 2u. Right? So 2 sine x as a first step. times the derivative of u itself. U is sine x. So the derivative of sine x is cosine x. Cool? Very, very important problem. These kind of things, the trig functions being raised to some power other than 1 are very common occurrences, and I want you to be very careful about them. Okay, there's another kind of common problem like this. ddx of e to the ax will show up in a whole bunch of places. For example, you may have e to the 3x, e to the 5x, e to the 7/3 x. So what's the derivative of e to the ax? Well, look at it this way. Is that simple e to the x? No. Because it is not a simple e to the x, whatever it is raised to, e to the something complicated, well, that complicated thing, make it into a u. So look at this as e to the u, with u being ax. As simple as that. So e to the u, the derivative with respect to u is e to the u. So as a starting point, e to the ax. But be sure to multiply by the derivative of ax itself, which is a. So this makes this a e to the ax. Cool? Alright. Now, similarly, you will end up with the derivative of sine of 7x, sine of 15x, all kinds of things like that. What do you do in a case like that? Same thing. This is not a simple sine x, so think of it as sine of u. The derivative of sine of u with respect to u is cosine of u, so that is cosine of ax, times the derivative of ax itself, which is a, making this a cosine of ax. Right? 7. What about derivative of cotangent of ax? Similar idea. Think of this as cotangent of u. Okay, cotangent of u. Wait a minute. What is the derivative ddu of cotangent u? Or if you remember in terms of x, what is ddx of cotangent x? That's negative cosecant square x. So the derivative of cotangent of u should be negative cosecant square u. That means here u is ax, so you have negative cosecant square ax times the derivative of u itself, that is times the derivative of ax itself, which is a. I sincerely hope you're getting the hang of it. You got the hang of it by now. All right. Otherwise, go back, watch all the rest of the argument, and make sense at each and every step. All right. So this is negative a cosecant square of ax. Now, I'm going to make it just a tad more complicated. ddx of secant of e to the 2x minus 3. Okay. What does it look like? Does it look like secant u? It has to look like that. It has to look initially like, we got a secant of u. Cool. Secant u, the derivative with respect to u is secant u tangent u. Oh, okay. So secant of u happens to be this e to the 2x minus 3, stuff inside the parenthesis. So secant u tangent u, secant of e to the 2x minus 3 times e to the 2x times tangent of e to the 2x minus 3. Right? Secant u tangent u. We're not done yet. Now what do we need to do? We need to multiply that by the derivative of u itself. What is u? The stuff inside the parenthesis. E to the 2x minus 3. What's the derivative of e to the 2x minus 3? Uh-oh. The derivative of e to the 2x minus 3? Man. I know the derivative of e to the x, but e to the 2x minus 3? Yeah. Well, haven't we done things like this before? E to the derivative of e to the something. Look at this problem too. We did e raised to x squared plus sine x. How did we do that? Well, we thought of this as e to the u, and then said e to the u times the derivative of u itself. Is this problem any different? No, except that this time we have to apply chain rule once again. To get to this stage, we applied the chain rule, and to differentiate e to the 2x minus 3, we have to apply the chain rule again. Oh, can that happen? You bet. So, what's the derivative of e to the 2x minus 3? Now, we already said u is this guy. How about this? Look at this as e to the u1. Cool. E to the u1. What is e to the u1, the derivative, with respect to u1? E to the u1. Right? What is u1? 2x minus 3. So there we go. E to the u1. E to the 2x minus 3. Are we done? No. Be sure to multiply this by du1 dx. Meaning ddx of the derivative of this 2x minus 3 itself. The derivative of 2x minus 3 is just 2. Alright? This is the idea. Now look at that. We applied chain rule inside chain rule. Okay? And that's entirely possible. In fact, there could be even more layers. And I'll probably test you on a few more layers. So be prepared for it. All right. Tangent to the 8 of 5x. Ooh, tangent to the 8 of 5x. Did we encounter somewhat of a similar scenario before? And did I mention anything about something like this? I said if a trig function is raised to a power other than 1, as is this case, tangent of 5x is being raised to a power of 8. So immediately think of this as tangent of 5x, the quantity raised to 8. Write it like that. If you can do that in the head, that's fine. Otherwise, shamelessly go ahead and write. No big deal. Now what is this looking like? This at this time should be looking like u to the 8. Cool. What's the derivative of u to the 8? 8u to the 7. Power rule. Right? 8 times u happens to be tangent of 5x. 8 tangent of 5x. 8 times the quantity tangent of 5x raised to 7. Okay? Times the derivative of u itself, where u is, don't forget, I mean, I know I can keep, for some reason I'm used to keeping track of all of this stuff in my head. Okay, what's my u? Tangent of 5x. But if you need to go to the side and write down u equals tangent of 5x, go ahead and do that. And once you're done with the problem, erase that, you strike it out. So that, when you go to the next problem, you don't confuse this one with the previous one. Okay, so tangent of 5x, that's a u. So we need to multiply this by the derivative of u itself. That means the derivative of tangent of 5x itself. What's the derivative of tangent of 5x? Oh, wait. Tangent of 5x? Man, that's not just a tangent of x. Okay, cool. Tangent of u1? You want to think of it as tangent of u1 with u1 being 5x? Yep, you can do that. So what's the derivative of tangent of u1 with respect to u1? Secant square u1. That means secant square of 5x. Are we done? No. We need to multiply this by the derivative of u1 itself, which happens to be 5x now. So the derivative of times the derivative of 5x is just 5. So times 5. Cool. Moving along. Yikes. Whoa, Nelly. Yeah, this is a good one. What should you look at this as? You should look at this as square root of some u. Excuse me. What should you look at this as? ddx of some square root of u. Okay, what is u? Here, please pay extra special attention to this problem. Losing track of u's is a very possible thing here. So, u happens to be everything under the outside that big radical. That means x plus square root of x plus square root of x. All this stuff is u. If you need to write it down, do so. Cool. What is the derivative of ddu of square root of u? As a first step, look at it as square root of u. So the derivative of square root of u with respect to u itself would be, do you remember ddx of square root of x? 1 over 2 square root of x. I wanted you to memorize that one. It's because now look, it shows up in many places. So please memorize that. ddx of square root of x is 1 over the quantity 2 times the square root of x. So with u being x plus square root of x plus square root of x, this stuff inside the big radical, the derivative would be 1 over 2 times square root of u. But u is this guy. So you end up getting this as a first step. Are you okay with this? Let me repeat that. Look at this as square root of u. U is all this stuff. And the derivative should be 1 over 2 times square root of 1 over 2 times the square root of whatever the u is. U happens to be the stuff under the big radical. That's exactly what I wrote. At this stage, my u is this stuff only. Cool. Next step. We need to multiply this by the derivative of u. Can you look at the stuff inside the radical and say, what's the derivative of this? Well, you have a sum, x plus something, and a big square root. Okay, we can do the derivative of each and add them up. This because the derivative of a sum equal to sum of the derivatives. Cool. What's the derivative of x with respect to x? Just 1, right? So the first part is piece of cake, 1, plus. Now we need to take the derivative of this guy with respect to x, ddx of square root of x plus square root of x. Whoa. So now look at this as, in the process of taking the derivative with respect to x, look at this as square root of u1, with u1 being what? X plus square root of x. Look at this as square root of u1, where u1 is x plus square root of x. Okay? Okay, so 1 plus 1 over 2 square root of u1. Right? What's the derivative of square root of u1? 1 over 2 square root of u1. 1 over 2 times square root of u1. That's what I did. But then we need to multiply this by the derivative of u1 itself. That means the derivative of this guy, x plus square root of x. The derivative of x is 1. That's what I wrote here. Plus the derivative square root of x is 1 over 2 square root of x. Is that complicated? You bet. But that's going to be the nature of these kind of problems. You have to get used to it. That's why you have to do every single problem in this section. You must master chain rule. Okay? What else? ddx of a to the x. ddx of a to the x? That's big time not equal to. Oh, big time not equal to what? Oh, man, we already know ddx of e to the x is e to the x. E is a constant. Here a is a constant. So just like e, this is just, ooh, dang, I didn't even think that people could think like that. Ah, got it. So some people do. So let me warn you against this. What is it big time not equal to? Oh, man, the power rule. Let me apply power rule. The derivative of x to the n is nx to the n minus 1. So here, xa to the x minus 1. No. Big time not equal to. Okay? What else? ddx of a to the x is big time not equal to, just like ddx of e to the x is e to the x, so a to the x is a to the x. No. That's not true either. Right? So what's the answer? For that, we need to recall something. Do you know what e to the natural log of x is? E to the natural log of x is just x. Cool? E to the natural log of x equals x. So that means wherever we see e to the natural log of x, we can just replace that with an x. But would we ever be so crazy as to look at a simple x and say e to the natural log of x? That would be crazy, right? I mean, it's like looking at 5 and saying, hey, you mean e to the natural log of 5, man? I mean, imagine, like if you went to a friend and said, hey, can I have $3? You say, hey, can I have e to the natural log of $3? That would look so weird. If one of my friends would slap me, I think. Cool. Let's get serious. Sorry about the jokes, man. Recall that e to the natural log of x is x. So the thing is, in some instances, it actually helps to look at a simple x as e to the natural log of x. For example, x equals e to the natural. When we look at a to the x, let's not look at it as simple a to the x. Let's give it this complex idea. That means we're going to call it e to the natural log of a to the x. Ooh, isn't that interesting? A simple a to the x, we will write it in a slightly more complicated version, e to the natural log of a to the x. Of course, they're both the same. E to the natural log of ax is what? A to the x. But on purpose, we'll write like this. Why? Because, notice, natural log of a to the x, there is this law of logarithms, rule of logarithms. This x now actually can become the coefficient. And so we can write this natural log of a to the x as e raised to x times natural log of a. Do you agree? That properties of logarithms, natural log of a to the x, well, becomes x natural log of a. That's the idea. Okay, what good did that do, man? It did a whole lot of good. So, does this look like e to the u? Now, does it look like e to the u? Yeah. So, what's the derivative of e to the u with respect to u? E to the u. That means e to the x natural log of a. Right? What else do we need to do? Oh, then we multiply by the derivative of u itself. That is, we multiply by the derivative of x times natural log of a. Natural log of a is a constant. So constant multiple. We'll pull that constant multiple out. So we have natural log of a times the derivative of x itself, which is 1. So we have a times natural log of a. You good? Let me repeat that. This is e to the u to me. That means its derivative, first step, is the derivative of e to the u is e to the u with respect to u. So e to the u times the derivative of u itself with respect to x. The derivative of x times natural log of a with respect to x is natural log of a, I can pull that out, times the derivative of x, which is 1. So that's why I have a simple natural log of a. Cool? But then we notice, hey, we had a to the x here, which we eventually wrote as e to the x natural log of a. Right? E to the natural log of a to the x, and that. So basically this e to the x natural log of a is nothing but a to the x. Do you agree with that? A to the x times natural log of a. Folks, I admit I am teaching quite a few somewhat heady concepts in this particular one. That's why I warned you. Please pay extra special attention to this one, and this is quite possibly the most important section in the entire calculus one. This, and when we get to almost toward the end, 5.5 substitution rule for integration stuff. These are the two things that I expect you to master. So take your time, watch the video thoroughly. Anyways, so what did we end up getting? The derivative of a to the x is a to the x natural log of a. Again, a result that you must memorize. At any time, if I say, what's d dx of a to the x? You should say a to the x natural log of a. Right? I don't know, did I say this here? Now, you must ask a good intelligent question at this time. Anybody? After getting this result, you should ask me an intelligent question. What is this a? Oh, a is just a constant. Okay. If that is the case, isn't that what we have when we have e to the x? We have a constant e. Instead of a, we have a e. E is just a constant, just like a is. So how come we don't say we don't do what we did? According to this, shouldn't we say this is e to the x, just as a to the x, times natural log of a? Instead of natural log of a, we say natural log of e. Shouldn't we say that? You are right. Yep, we should say that. But how come we don't say that? We just simply say e to the x. That's because what is natural log of e equal to? That's 1. So e to the x times 1 is e to the x. That's why we would be multiplying by 1, and that's why we don't bother. Cool? All right. Next. What's the derivative? Ooh, I like this. d dx of 4 to the 3 to the 2 to the x. What does it look like to you? Does it look like 4 to the u? It has to. So, as a first step, look at it as 4 raised to something complicated. Cool. If it is complicated, if it is not a simple x, complicated, more complicated than that, u. 4 to the u. Cool. 4 to the u with respect to u. Right? 4 to the u with respect to u is 4 to the u natural log of 4. That means 4 to the 3 to the x times natural log of 4. Are you okay with that part? First part. 4 to the u. Derivative is 4 to the u natural log of 4. Cool. times the derivative of u itself. Excuse me. The derivative of u itself. What is u? U is 3 to the 2 to the x. 3 to the derivative of 3 to the 2 to the x. Wait, that looks like 3 to the u1 to me. Cool. 3 to the 2 to the x looks like 3 to the u1. We already said 3 to the 2 to the x was u. So let's call 2 to the x this time as u1 and call this as 3 to the u1. We need to find the derivative of 3 to the u1. Well, 3 to the u1, the derivative is 3 to the u1 natural log of 3. u1 is 2 to the x. Times the derivative of u1, which is that u1 is 2 to the x. So the derivative of 2 to the x. What's the derivative of 2 to the x? That looks like a to the x. So 2 to the x times natural log of 2. Will I ask questions like this in test? Oh, you bet. You bet. So we will work. You better work on this one and bring a whole bunch of questions to class. And when you get to this stage, I will be probably getting you to solve a whole bunch of problems in class, because I want you to master this one. All right, folks, I think that's it. Adios.